It is a pleasure to have Samuele Mongodi from Politecnico di Milano. We'll talk about Steinness problem. Samuele.
Okay, thank you. Well, thank you for the invitation to speak here. This is I want to present a collection of problems that I've been studying or thinking about, or whatever you may call it, in the last years. So I hope there is not too much material into this presentation, but we will see. So starting slowly, a Stein space is a space with a lot of holomorphic functions, meaning that global holomorphic functions separate points, and the moduli of global holomorphic functions separate a compact set from infinity. So the envelope of a compact set with respect to holomorphic functions is still a compact set. This is equivalent to various conditions: the celebrated theorems A and B by Cartan, the Debye equation, the solvability of the Debye equation, the existence of a strictly plurisobharmonic function, exhaustion function. This is due to Grauert in the smooth case and to Narasimhan in the singular case. And well, the last one is just a rephrasing of the two conditions, because the OX convexity is exactly the fact that the envelopes of compact sets are still compact, and the fact that it contains no compact complex subspaces but its own points is the fact that global holomorphic functions separate points. So, I mean, this is a pretty convincing description of what Stein space is. It gives a lot of ways to check if a space is a Stein space. Nonetheless, one could ask some questions. For example, if we just have an exhaustion which is plurisobharmonic but not strictly plurisobharmonic, what additional conditions ensure that the space is Stein? For example, what geometric conditions? Or more in general, and we will see it, what can we say about the geometry of a space which only has a plurisobharmonic exhaustion and not a strictly plurisobharmonic exhaustion? On the other hand, the Levy problem. So we have a domain inside our complex manifold. What conditions should we put on the boundary of this domain so that it's Stein? Or maybe conditions on the boundary and on the ambient space. So, I mean, in some cases, these questions are well known and answered, obviously. And the third one, which is actually very, very general in this formulation, when does a compact set have a basis of Stein neighborhoods? This is well, important in many ways. And actually, this kind of compact sets are sometimes called Stein compacts. And the fact that, mainly the fact that there are a lot of holomorphic functions on a Stein space means that, suggests that we can perform a lot of operations that usually are involve smooth functions or continuous functions, because they are more, they are less rigid. But on a Stein space, usually we can do that also with holomorphic functions, so approximations, result, and stuff like that. So I would like to start with the first kind of question. I mean, these are not really precise questions. These are more like lines of thought. So the first subject I want to talk about is the kernels, the minimal kernel actually of a weakly complete space. But anyway, let's consider a non-compact weakly complete space. So a space with a smooth plurisobharmonic exhaustion function. The Riemann reduction of a space is a quotient of that space by an equivalence relation obtained identifying points where all the holomorphic functions are equal. This again gives a complex space, and the equivalence classes are compact complex subspaces, if the space is, well, holomorphically complex. So an idea could be, let's do the same thing with pluribus harmonic functions. By the way, doing it with pluribus harmonic functions or pluribus harmonic exhaustion functions is the same if you assume that the space is weakly complete, because you already have one exhaustion, so you can always sum it to another function and get another exhaustion. So we define these sets, the equivalent classes of these relationships, that are the points such that all the pluribus harmonic functions agree on those 2 points. If you don't obtain just the singleton with x inside, you can actually show that this point is a point where the Levy form of every pluribus harmonic function degenerates. This has been shown by Zlotkowski in a recent paper that we published. Maybe I wrote 20. I'm not exactly sure because it. I mean, it was a seminar he gave like 3 years ago, then got published in the collection of the seminars. Internet is not sure about the, the year of publication. Maybe it's 19. Anyway, this is a sort of the same procedure that you would do for the Remet reduction. Point is that pluribus harmonic functions are not as well behaved as holomorphic functions. So, for example, you don't know that these equivalence classes are, I don't know, complex subspaces. You know they are compact and they are closed, but other than that, an object that helps studying this this problem is the kernel or the minimal kernel of the weakly complete space X. It was defined by Zlotkowski and Tomassini in a paper in 2003, 4 probably. I'm getting all the dates wrong anyway. And this is the set of points where all the Levy forms of all the pluribus harmonic functions degenerate. So the set of points where no pluribus harmonic function can be strictly pluribus harmonic. For example, if you blow up C2 at the origin, you add a projective line, which is a compact analytic variety. And on this compact analytic variety, all the pluribus harmonic functions are constant, so their Levy form degenerates. If you take C times a compact curve, so a space that is a product between a Stein space, for example, and a compact space, along the compact fibers, all the pluribus harmonic functions again are constant, so the Levy forms degenerate. In general, what can we say about the geometry of this set? Well, we have.
Excuse me.
Yes.
Samuele, I have a question. I'm sorry, it probably is a stupid question, but you talk about the Levy form, or you mean the complex Hessian?
The DDC of phi.
So is the complex Hessian? I mean, do you evaluate also only on the I mean, do you evaluate it also on the complex transversal direction?
You don't have anything that is transversal. I'm talking about the whole space. So you have a complex manifold.
Okay.
You're not on the boundary of something.
Okay.
So that's why there is no difference between the Levy form. I mean, you can call it Levy form or complex Hessian. It's because it's actually the same thing. So
okay, thank you.
No problem. So in this part, you don't have the boundary of a domain. You just have your complex manifold. So the tangent is a complex vector space, and DDC of a function is a bilinear form on this vector space. Obviously, I mean, one step at a time. If this set is empty, it means you have it means that you can actually build a pluribus harmonic function which is strictly pluribus harmonic everywhere. It's not immediate, but I mean, you can do it by patching the various pluriharmonic functions. And so the weakly complete space is Stein, because if you have a pluriharmonic function, you have a strictly pluriharmonic function, you have a pluriharmonic exhaustion function. In general, we have a minimal function that is a pluriharmonic function whose DDC degenerates at exactly only the points of the kernel. So we can build a function that is strictly pluriharmonic outside this set. So both the equivalence classes we were talking before, these equivalence classes for the values of pluriharmonic function and the intersections of the kernel with the levels of the minimal functions are local maximum sets or one pseudo-concave sets. What does it mean, local maximum sets? It means that locally the maximum principle holds. So for every point there is a neighborhood such that the intersection of, if you take any pluriharmonic function, its maximum is reached on the boundary of the intersection between your set and this neighborhood. Again, X is Stein if and only if the kernel is empty, which then means if and only if it does not contain any compact one pseudo-concave set or any compact local maximum set. And, well, this is an easy consequence. X is a modification of a Stein space if and only if the kernel is compact. If and only if the union of all pseudo-concave sets is compact, if and only if the union of all local maximum sets is compact. By the way, in case 2, this set is empty. In case 3, you are actually showing that the kernel is a union of compact analytic varieties inside of X. So in case 3, the kernel has actually an analytic structure, a complex analytic structure. So you could have a sort of a side question or side quest if you play video games, asking, does this kernel have always any kind of geometric or complex analytic structure? So in the case of complex surfaces, first of all, thanks to a result by Sherbina, you can show that the intersections of the kernel with the level sets are foliated in analytic disks. Now, if you follow one of the leaves and this closes up, you have a compact complex curve inside a level set. With some, technicalities, you can move this curve around and you can obtain uncountably many curves, always inside the level of the exhaustion function. And by result, by Nishino, this means that X is actually a union of compact complex curves. Moreover, if a whole level set is contained in the kernel, so if this intersection is actually the whole level set, and it does not contain any compact curve, then this level set is Levy flat and foliated with dense complex leaves. So if no leaf closes, then all the leaves are dense. So you can build examples from Hopf surfaces or quotients of C2 by a real three-dimensional lattice with the right with some generating vector Q independent from the others. And in general, in any dimension, if a level is contained, then some levels below it are still contained. So if you have one level inside the kernel, so if there is a whole level of an exhaustion where no function is strictly pluriharmonic, then you have a whole collar, a whole annulus where no function is strictly pluriharmonic. And this is true in dimension 2. This is a part of a work, well, what I'm talking about here are works in collaboration with Giuseppe Tomassini and Zbigniew Zolotkowski. So some more results. If the surface has also a real analytic exhaustion, then all the levels of the exhaustion have the same structure. So you have only three choices. X can be a modification of a Stein space. X can be union of compact complex curves, or X is foliated in Levy flat hypersurfaces with dense complex leaves. So in the third case, X is a union of Levy flat hypersurfaces, three-dimensional, with dense complex leaves. Moreover, X cannot contain any positive curve, which means a curve with positive self-intersection. Well, that's just because you couldn't have any Paris harmonic non-constant function in a neighborhood. It can obviously contain negative curves, so you simply blow up a point. If it contains a curve with zero self-intersection, then you have two cases. Either X is a union of complex curves, or a neighborhood of this curve is foliated again in Levy flat hypersurfaces with dense complex leaves. What happens, for example, in a Hopf surfaces around one of the two compact curves? Again, if we have a real analytic plus harmonic exhaustion, if you take any weakly complete domain inside of X, so a smaller open set, which is still weakly complete, you have only two choices. You either have a modification of a Stein space, or you have something which has the same type, the same structure of X. Lastly, another thing you can show using these kernels, if you take any complex manifold and a pseudo-convex domain in this complex manifold with smooth boundary, if the boundary of the domain has a neighborhood with empty kernel, then the domain is a modification of a Stein space. So you can build a Paris harmonic exhaustion for the domain, which is strictly Paris harmonic near the boundary, which means it can have some compact kernel inside, and then it's a modification of a Stein space. What does the hypothesis on the kernel mean? The kernel of the boundary simply means, it means to take any open neighborhood on the boundary and take the kernel. So the point where all the Paris harmonic functions are not strictly Paris harmonic. You are not asking anything about exhaustions. Here there is nothing which is weakly complete, so it's just all Paris harmonic functions. So it actually boils down to say that there is a strictly Paris harmonic function near the boundary. Now, you can ask a lot of questions about this. Obviously, we did everything. I mean, the structure of these spaces is completely known, well, at least fairly well known, in dimension 2 when the exhaustion is real analytic. Or in dimension 2 when a whole level sits inside this kernel. So the first question is, what can we say in dimension 2 when the kernel intersects a level not in the whole level set, but just in some part of it, and this part is not a complex curve. So we cannot rule this possibility out. Well, question 2 is a leftover of a slide I removed, but there is an example by Brunella of a weakly complete space without any real analytic exhaustion, Paris harmonic real analytic exhaustion. And this space by Brunella has that weird structure of Levy flat hypersurfaces foliated with dense curves outside the compact. So this is a weakly complete space, which outside the compact has actually a real analytic exhaustion function. So outside this compact, it is a it falls in one of the three cases, but we cannot understand what happens inside that compact, how big that compact can be, and the example is actually quite concrete. So I mean, it's not an existence theorem; it's a real example. Another question is what happens in higher dimension. So in the techniques we use here, for example, the Sherbina result that gives us this foliation in disks and Nishino result about the foliation in complex curves are all linked to dimension 2. So we don't know anything of similar to these two results in higher dimension. I mean, you cannot just export the scheme of the proof. Also, it is not clear that the three behaviors we identified are the only ones possible if we are in dimension 3 or 4. So anything in higher dimension is a question, actually. Another question, which is a bit more technical, is the following. I mean, the result by Sherbina actually is employed because of that observation that these intersections of the kernel with the level sets have this local maximum property, R1 pseudo-concave sets. This is how we can use the Sherbina result about foliation of graphs. So is there any kind of geometric or analytic structure that can be given to local maximum set or one pseudo-concave set? So in general, if we have something like a local maximum set, which behave a lot like analytic sets, can we give it a complex analytic structure, some geometric characterization? And obviously the last question is, well, these are all about the first kind of question we talked in the beginning. The last question is about the second kind of question, so the Levy problem. We have a domain, we have a domain in a complex manifold, it's the complex domain. We suppose that there exists a neighborhood of the boundary which has an empty kernel, but if you go through some examples, you will notice that the sensible choice for an hypothesis would be that the kernel of the domain is bounded away from the boundary. So you don't know that the domain is weakly complete, so you don't have any exhaustion. You just know that the boundary is pseudo-convex and the kernel inside the domain is compact. So it does not intersect the boundary. What can we say about omega? So the claim would be that omega is again a modification of a Stein space. However, I don't know. Because this kind of hypothesis doesn't give you a strictly parasomorphic function on the whole neighborhood of the boundary. It just gives you a strictly parasomorphic function inside the boundary, so on one side of the boundary. This doesn't seem enough to employ the usual techniques. But in the spirit of giving these objects some analytic structure, there is an interesting definition by Sibony, the Levy currents. So a Levy current is a non-zero current, which is of B dimension 1,1, so it acts on 1,1 forms. It's positive, DDC closed, and its wedge with the DDC of any continuous parasomorphic function vanishes. For example, the integration on a compact complex curve. Now, if
Samuele, just a question, can you remind me what a current is, which I forgot?
Well, briefly, it's a function along forms. So, for example, the integration on a submanifold is a current. The integration against a vector field is a current. So, I mean, here currents are mainly thought as weak versions of complex submanifolds. So, I mean, you would like to say complex curve in this case. It's not really like that, but for example, another kind of object that respects this condition is the integration along along a Levy flat hypersurface just in the complex direction. So you take a three-dimensional Levy flat hypersurface, which is foliated with complex leaves, and you integrate along the leaves. if you have a form, a 1-1 form, and integrate along the leaves, you get a function. You have just to choose a transverse measure to complete the integration. And if you choose a harmonic transverse measure, you get the second condition.
If I may give a tentative answer as an analyst, is a form value distribution.
Or a distribution valued form. Depends how you switch it. Yes, so it's a general. Distributions acts on functions. Currents acts on completely supported differential forms in the same way. Asking for positivity is a strong condition, like when you ask for a measure to be positive, it's quite a strong condition. So you get, for example, finite masses, locally finite mass, etc. Okay, so moreover, if T has compact support, the last condition, which is a bit non-standard, follows from the first two. So actually, if T has compact support, you don't have to worry about the third condition. Levy currents were introduced by Sibony in a paper 3 years ago. But actually, you can find things very similar to them in previous papers, always by him. The main, not the main idea, but one nice idea about employing Levy currents is the following. You use a sort of duality. So you take a compact set inside of X, your manifold, and you consider an Hermitian structure on X. I consider this set, the set of currents, which are positive, 1, 1. The support is inside the compact K, and they have mass 1 in a way. So you normalize them. This is a very nice closed convex set. And you define this other set. So the orthogonal of the DDC of test functions on X. So this is the set of DDC closed currents, because it's the orthogonal to the DDCs, so it's the set of DDC closed currents by just integration by parts. If there exists no Levy current on K, it means that these two sets have empty intersection. So no current of the first set is inside the orthogonal to the DDCs of test functions. By Banach, they are strongly separated. That means that you have a function here such that the DDC of that function against T is greater or equal than a constant which is strictly positive for all T in this set. Which means, if you do your computations, that the function U is strictly Paris harmonic on K, on the compact K. So the non-existence of Levy currents is linked to the existence of strictly Paris harmonic functions by this duality argument, which is sketched here and is sketched as well in the paper by Sibony, actually. But he gives references to places where it's carried on more thoroughly. So what can we show with these Levy currents? Well, for example, if you have a domain with real analytic boundary, then the boundary does not support any Levy current if and only if it contains no germs of holomorphic curve. Here, real analytic is very important. If X is weakly complete, then it's Stein if and only if it contains no compactly supported Levy current. If you have an open pseudo-convex domain, the boundary does not support any Levy current, then omega has positive uniformness index, hence is a modification of a Stein space. And again, if you have something which is weakly complete, which is not a modification of a Stein space, and with finitely many compact complex varieties of positive dimension, all the level sets of the exhaustion contain a Levy current, at least after some point. So if you, I mean, there are other applications of these Levy currents that are contained in Sibony paper, but we are focusing on these ones because they remind very closely the kind of results that we can get with the kernel. So the suspicion that arises from these results is there a link between the support of the Levy currents and the kernel? So why one should ask this kind of question? Because the kernel is just a set, so it's a set of points. The currents have much more structure. The currents are a set of points where I give, for example, a vector field and a measure, or a distribution of tangent directions and a measure. I mean, you can wrap it up as you like, but you are putting more structure than just a set. Again, not really, because if you think it carefully, the kernel is where all the pluribus harmonic functions are not strictly pluribus harmonic. It's easy to show that it means that at every point there has to be at least one common direction where all the complex actions degenerate. So actually the kernel does give you a distribution of tangent directions. But anyway, still it doesn't give you a way to integrate against this. It doesn't give you a measure to build actually a current. Acting on this suspicion with Fabrizio Bianchi, we investigated the matter and we wrote a paper which is now, I mean, being evaluated for publication. And we could show a bunch of things. Among those, if you take a wiki-complete manifold and exhaustion function and the regular value, first of all, the intersection of the kernel with the level, if it's non-empty, it contains a Levy current. Moreover, if the dimension is 2 and the level set is completely contained in the kernel, then the whole level set is the support of a Levy current, obtained by integrating against d phi wedge dc phi. Again, if in dimension 2 we can choose the exhaustion real analytic, then again the kernel is the union of the supports of the Levy currents, and the extremal Levy currents, meaning the currents which cannot be decomposed in smaller pieces in some sense, or which cannot be obtained as a combination of other currents, are given by integrating against the form this d phi wedge dc phi on either complex curves or Levy flat hypersurfaces, depending on the structure of X. In general, from the first point, you just have that the support of all the Levy currents are contained inside the kernel. You don't know if they are equal or not. So you have, again, a bunch of questions. And the first one is obviously if it's true or not that the kernel is exactly the support of all the Levy currents. A partially related question is, if you take the support of a Levy current, can you give it some geometric analytic structure? Because in the cases we could analyze, so dimension 2, these Levy currents were almost always the integration along some complex curves, either compact or leaves of a Levy foliation. Question 1.70 is a bit weird, but if you think about it for a moment, kernels and Levy currents are easier to handle if you have a lot of holomorphic vector fields, because if you have holomorphic vector fields, you can push things around holomorphically. So the question is, can we say something when the space is infinitesimally homogeneous? For the Levy currents, the answer is yes, and it's contained again in Sibony paper. For the kernel, probably the answer is again yes, but it's not done. And but I mean, infinitesimally homogeneous is not the only reasonable hypothesis. Maybe you could consider other kinds of spaces where you have some holomorphic action. And the last kind of question is related to the Levy problem. So if you don't have any Levy current in the boundary, you have Diderot for next index positive. Can we think about similar objects that realize an obstruction to have a Diderot for next index 1? So to have a defining function which is Floris harmonic in the neighborhood? Because obviously, if you have a Levy current in the boundary, I mean, for example, if you have a compact curve in the boundary, obviously you cannot have a Diderot for next index 1, but for example, Levy currents do not see a disk or an annulus in the boundary. And this brings us to the third kind of topic, so the Diderot for next exponent. The Diderot for next exponent is the following. We take an open convex, pseudo-convex domain, bounded and smoothly bounded, and we suppose that it's given by a defining function. We can ask if there is some power of this defining function which is Pluris harmonic on omega, or at least on a on some part of omega close to the boundary, for some eta between 0 and 1. Well, obviously 0 is not a very interesting choice. The supremum of such eta is called the Diderot for next exponent of omega. What I'm going to talk about is joint work with Gianmaria Dallara, which is still work in progress. Actually, Gianmaria talked about it a bit almost 1 year ago, so it's been a slow progress. Now, I would like to present a construction which is a bit abstract, so I didn't want to give it in full detail. I hope it's enough to understand. We consider the Levy null distribution, so the distribution of the kernels of the Levy form, in the sense Marco was referring to before, so the Levy form on the holomorphic tangent of the boundary, so the maximum complex subspace of the boundary, of the tangent to the boundary. And so N is this distribution of kernels. And S of N is the support, so is the place where N is not just the trivial kernel. So if, for example, omega is strictly pseudo-convex, then S is the empty set. The reduction we want to study is the following. We take for any point N of X, so the kernel on the point X of the Levy form, and we intersect with the maximal complex subspace of the tangent space to its support. What does it mean, the tangent space? Is the Zarinsky tangent space in this infinity constant. So you take the vector fields that are annihilated by the differentials of the functions that are 0 on the set. The Zarinsky tangent, so m over m squared dual. The core of the Levy null distribution is the limit of this procedure. So you keep iterating this procedure, obtaining smaller and smaller possibly distributions, and obviously these possibly could alter the support of the distribution, because maybe at some point the tangent to the support is a totally real subspace, for example. Or I don't know, there are quite easy examples of pseudo-convex boundaries where the points where the Levy form degenerates are a real curve. So the tangent is obviously totally real. And so once you do one step of this procedure, you end up with an empty set. But in general, this procedure stabilizes up after, well, possibly countably many iterations. So you should define it via transmit induction, but anyway. the core is the limit of this procedure. So the core is a distribution of subspaces of the kernel of the Levy form, such that the support of this distribution, the tangent to the support of the distribution, intersects at every point the corresponding subspace of the kernel in a complex subspace. Why doing this kind of effort? Well, there is a quite interesting object, which is the D'Angelo form of the boundary, which is defined as follows. Take a vector field such that dCRT is 1, means that the vector field is transverse to the to the holomorphic tangent. Alpha is the lead derivative along T of dCr. Well, alpha is we want to look at the form alpha, which is a 1 form, only on the distribution, on the Levy null distribution. So what we can say that alpha is well defined. It doesn't depend on the choice of T or even of R, and closed as a 1 form on the Levy null distribution. We define this quantity, which is the infimum of the positive number, such that this 1 form is bounded by T times the d bar of alpha, which is again a 1 form, on n, obviously, because on the Levy null distribution, because outside of it, the alpha is not even well defined. And well, n of n is the infimum of all the possible choices of T and R in the definition of alpha. So all the possible alphas. This quantity actually estimates, not estimates, but gives you the Diderot-Furness index. It is a result by, I mean, it's been proven bit by bit during the last 3 years by Liu, Hume, and finally a paper by Adachi and Hume. The Diderot-Furness exponent is given by 1 over 1 plus n of n. What is interesting is that this quantity we just defined is stable when we reduce the Levy null distribution to its core. So when we do that whole procedure of intersecting with the complex subspace of the tangent of the support. And we have some consequences from this result, from this reduction to the core. But mainly, the point is that we can only look at the core. So, for example, we immediately prove that on weakly regular domains, well, immediately it's not that hard to prove that on weakly regular domains, which are domains with some properties. I mean, I don't want to enter the definition of weakly regular, but actually it means that the points where the Levy form degenerates on the boundary have a structure which is, I mean, in some way there are a union of totally real pieces. So on weakly regular domains, after a finite number of steps, the core becomes empty. The support of the core becomes empty. So on weakly regular domains, you don't have anything here to take the infimum on. So this is just 0, and you get 1. On the other hand, if you have any piece of analytic curves, analytic variety inside the boundary, this piece will be stable under this reduction, so you will end up with estimating this infimum on the vectors which are tangent to some analytic variety. So you actually define not really a norm, but a function which is almost a norm on the cohomology of the degree 1 cohomology of analytic curves, the complex curves in the boundary, which is actually a way to reinterpret the first work by Liu, which was just about the worm domain. And he would estimate this kind of norm for the annulus contained inside the boundary of the worm. Thirdly, local maximum sets are contained in the support of this core, which gives this support some sort of analytic structure. Not really, but anyway, these are the kind. You can the work in progress with Gian Maria contains also other kinds of results, but these are the ones I would like to focus on now. I think it's already maybe too much. And these are the related questions that stem from those. Does the support of the core have any analytics, or really, actual analytic structure? So being a local maximum containing inside the local maximum set is nice, but well, a foliation structure would be nicer, for example. We define some sort of norm on cohomology. There are other kinds of norm on cohomology defined in similar situations, for example, by Bedford and Furness. And so can we estimate these norms? Are they equivalent? Are they not equivalent? Again, the support of the core of the Levy null distribution contains all local maximum sets, but is it a local maximum set? Well, we don't know. And the last question, the 2.6, is a tricky question because on the paper, this procedure for reduction to the core can take as many steps as you want. You can cook up examples when this procedure lasts as many steps as you want, even infinitely many steps. But usually, these examples all have trivial D'Angelo forms, so it's useless because the estimate you could give it in the beginning. So it's no use to reduce the set. So are there any interesting examples where this reduction is really useful in order to estimate the D'Angelo form, the norm on the D'Angelo form? And obviously you can ask you can flip out inside out the question. So you can ask, okay, we looked at the Diderot-Furness exponent. You can talk about the Steinness index. I think that's how Jung calls it. So you close from outside and actually obtain a Stein neighborhood basis for the boundary. And again, you can ask the same kind of questions. A particular case when all these techniques become a bit imprecise is when the set of the support of the Levy null distribution is too big. For example, if you have a Levy flat boundary. So if you have a Levy flat boundary, you are forced to, very down to earth, you are forced to define a lot of stuff with less than or equal to instead of just less than, or well, the corresponding thing with greater than. And this gives you some kind of problems. Some equalities become just inequalities and you don't have all the results you would like to. So the last 5 minutes, which I hope I have, I would like to talk about semi-holomorphic foliations, which are, a generalization of Levy flat hypersurfaces, are just foliations which have complex leaves, which vary in just a smooth or real analytic way. So the local model is Cn times R to the D, and transition functions are holomorphic on the Cn component. When D equal 1, we get Levy flat hypersurfaces. And as I was saying, the previous estimates on the Diderot-Furness index are not that do not give accurate results and informations in some respects. And the problem with Stein neighborhood basis has to be confronted with other means. So this is what we did with Tomassini in a couple of papers from like 5 years ago. And we need two definitions. So, well, the first one is almost obvious. We need some convexity along the leaves. So we have leaves which are complex manifolds, and we ask these manifolds to be pseudo-convex. So we have a pseudo-convex exhaustion along the leaves. We also need some positivity in the transversal direction, and we define this by giving a metric on the normal bundle such that this inequality holds with K positive. I forgot to write that. If you compare this inequality with this one, you will see that it's more or less the same thing. Particularly if you interpret X as the boundary, as the Levy flat boundary of a domain. If X is zero analytic, transversal pseudo-convex, and positive with K equal 1, we can embed X in its own complexification and see it as the zero of a Pluribus harmonic function, which is strictly Pluribus harmonic outside of X. So this gives a Stein neighborhood basis for the compacts of X. There is a real analytic hypothesis which is not at all trivial, and also the this relation with K equal 1, which again is not trivial. Some consequences are approximation theorems on the compact sets of X for CR functions, vanishing theorems for cohomology, embedding theorems, and some sort of Oka principle for some classes of line bundles. I should say that the problem, I mean, a similar problem for just smooth Levy flat, smooth semi-Holomorphic foliations, smooth Levy flat boundaries was tackled by Forsnerich and Laurent Thiebaud with quite different means, but I mean, there are some resemblances. We need the real analyticity to build a pluriharmonic function. They build a I don't remember the name, but I mean asymptotically pluriharmonic function, something like that. A function whose DDC tends to 0 together with its derivatives when you approach your set. But then they use a lot more of the study of the geometry of the foliation, so it's kind of a different result. Again, you can formulate a lot of questions. For example, can we lessen the question K maybe not passing through a pluriharmonic function, but just a function with some vanishing of the DDC along X with some order or something like that. Can we use the same techniques in the smooth case, not obtaining everything obviously, but can we adapt the techniques to the smooth case? And the last question, we tried, because we tried to generalize the Oka principle to some that we found to some other classes of bundles, but it seems very, very complicated, at least via the techniques we tried to use. So this is just, I mean, an example of the kind of study that one can perform on Levy flat boundaries with respect to the, which always involves some estimates like these of the, this is a kind of, well, if you embed X as the boundary of something, this can be obtained as a D'Angelo form. So the D of the log of lambda. So you actually are estimating the same kind of thing I was talking before. Also, it should be worth mentioning that on a Levy flat boundary, you also have an upper bound on how much K could be. So it's not easy to produce big values of large values of K for which this inequality holds. It could be impossible depending on the dimension of X. But well, you can ask a lot of other questions, but I think this was all I wanted to say, so I will stop here. Thank you.
Okay, thanks. So there are questions, observations on this very scholarly seminar of
Devo salutare. A breve li devo salutare.
so someone was
It was a feint.
okay.
Maybe it was too much stuff in only one seminar.
No, it was let's see, next one. We need to learn. Okay, I have just an idea. Could you just make I don't know a list of examples of Stein manifolds, like to have an idea
Of Stein manifolds?
Yes.
Stein any actually it's a complete characterization. Any submanifold of Cn. So you take
any complex submanifold of Cn.
Yes, you take any the holomorphic equation you want in Cn equal to 0, okay. And zero. Actually, it's a complete characterization. Because you have a lot of holomorphic functions, heavy Stein manifold can be embedded into Cn properly.
Okay.
It's the so actually in Cn, a lot of these questions are trivial. I mean, well, not really, but if you have like a weakly complete domain in Cn, it's Stein. So a lot of stuff become easier in Cn. Also, the Diderot-Fornès paper, the original one was in Cn, and used the fact that minus log of the distance from the boundary is a plurisolomorphic function. So.
So there are no other.
Cn are pseudo-convex. Actually, is the same, no?
Sorry.
I mean, pseudo-convexity and Steinness for domains in Cn is the same.
Yes, completely. So if you have something which is the boundary, yes, it's the Levy problem in Cn. So if something is pseudo-convex on the boundary, then it's a Stein. It has a strictly plurisolomorphic exhaustion function. The whole point that in Cn is true, and you want to know what happens in more general situations. But again, in Cn, one way to see it, in Cn, you can act locally on the boundary and obtain something which is strictly plurisolomorphic on the boundary. And what happens next? You cannot have anything compact inside that prevents you from extending your strictly plurisolomorphic function. So it suggests that something like that should be true in general if you allow for compact objects inside, so modification of Stein spaces. So that's the whole. So the actual Levy problem one would want to tackle on a general manifold is you have a pseudo-convex boundary. You would like to show that maybe this is a modification of the Stein space. If you have some strict plurisolomorphicity near the boundary. So if you can do something near the boundary, you should be able to go inside and obtain. This is not. I mean, it's not clear at all. If you have the strict plurisolomorphicity all over a neighborhood of the boundary, inside and outside, it's true. And it's what we proved with Pino in the last paper, and it's what proves Sibony in a different way with different hypotheses about Levy currents in his paper. But if you have only the one-sided information, so inside the boundary, like you have a positive Diderot-Fornès exponent, I mean, it doesn't help.
Okay. Thanks.
Thank you again for the invitation.
Okay.
Just another.
Thank you so much.